I hope that you currently you are finished with revisions chapter 7. Please go through, read again the chapter 7. Just take main point that I told you, the last slide of the chapter 7, the trend of the property of the elements in terms of IE, EA, EMC, and what else? Atomic radius, that's it, properties. Alright, we continue chapter 8 today. Okay. Right, we can start new chapter. You ready?
Yeah, I'm ready.
Alright, please give your attention, focus, so that you can understand a bit. After this, you can do some more revisions. Okay. For chapter 7, chapter 8, or in your course outline is chapter 7 lah. Alright, same. The syllabus also not changed, but just I add up a little bit of slide in a few slide of in this chapter. And okay, so basically chapter 8, we focus on the bonding, chemical bonding. We have studied the reactions of we have studied the chemical reactions and then chemical equations, and how to calculate the electron energy of electron, the positions of electron in periodic table, what is the properties of the elements or of the valence electron in the periodic table. And now here come with the chemical bonding. Because we have studied the valence electron, the one thing, the important thing in the chemical bonding, which is the valence electron. Okay, chapter 8 basically we will look at the bonding between metal, non-metal, between non-metal and non-metal, and then metallic bonding between metal and non-metal, metal and metal. And basically the contents for this chapter 8, which is first one, the basic concept of chemical bonding. We have 3: covalent, ionic, and metallic. And then look at the ionic bonding, and then calculate the enthalpy of the energy change when atoms or compound dissociate to its elements or its gases atoms or its atoms. And after that we look at the size of the ions based on electronic configurations. We look at the size of the ions, what happen if in cation and anions form, what happens in the size of ions. And look at the after that, covalent bond, the main subtopic, which is covalent bond. If possible, I try to settle 8.1, 8.2, and 8.3 by today. And if after that, for 8.4, I will continue next class lah. Okay, for the covalent bond. Okay. And then 8.5 is Lewis structure. You know what is Lewis structure?
Oh yes, I know. It's SPM, where we draw like the electron structure, like the
Lewis structure. Lewis
like
structure means that
the dot around the alphabet.
Yeah. Dot representation is the Lewis structure lah.
Haven't seen this thing in a while.
Yeah, we will look at in details Lewis structure and how to calculate the formal charge of the Lewis structure for each element. You know formal charge? What is formal charge? You know what is formal charge?
What charge?
Formal charge.
No, I have no idea what that is.
Later we'll study how to calculate the formal charge for each elements using Lewis structure, doing dot representations. And last one is strength of covalent bond. That's it. So objective for this chapter 8, which is the first one, you are able to determine the size of ions and the lattice energy. And next is able to draw and use Born-Haber cycle for calculations of enthalpy, calculation of energy. Able to draw Lewis structure to fulfill octet configurations, octet rule. And next objective, you are able to identify resonance structure and calculate Former charge from resonance structure, and then able to calculate enthalpy, which is energy, from the Lewis structure of the components. Last one. And okay, first is a basic concept of chemical bonding. Okay, why atoms or elements or molecule undergo chemical reactions? Why?
To attain a stable configuration of electrons.
Yeah, to attain stable configurations. Atoms, elements or molecule, if they can choose, they are given an opportunity to choose, they will choose to achieve stable configuration. Like in group 18 noble gas, they choose to attain stable configurations if they are given opportunity to choose. Alright, so what is the octet configurations? Octet configurations like 1s2 to s2 to p6 equal to 10. 10 electron is Ne. So this is octet configurations. Octet configurations mean already full. No need to accept electron, no need to donate the electrons. Already stable, unreactive, already inert, achieve stable configurations. And so this is a reason why octet configurations, because stable configurations has a high ionization energy. Group 18, all the elements in group 18 are high in ionization energy, but within the group, when down the group, low ionization energy. And low affinity for the additions of electron, we cannot accept or donate any electrons in group 18 because it's already stable. And lack of the electroreactivity means that because of we cannot add the electron or donate the electron, means that there is no activity at all, no reactivity at all. Okay, so for the electron affinity, low electron affinity because we cannot add electron anymore. Group 18 is stable configurations, achieve octet configuration. So no need to add a valence electron with other valence shell with others electron, because already achieve stable, which is 8 electron on shell here. And high ionization energy because we cannot remove any electron from here. If we want to remove electron from here, we need a lot of energy, high in energy, ionization energy, in order to do that way. So stable configurations. Alright. So next, what is the octet configurations rule? Okay, so octet configurations rule is the stable or surrounded by the 8 electron. Now you have studied this to achieve stable configuration for, except for helium, all valence electron must achieve octet configuration or 8 electron.
Okay.
Okay, so 4 pair of valence electron arranged around the atoms means that 4 pair means that electron 1 pair, 2 pair, 3 pair, and 4 pair, isn't it? So 4 pairs of electrons equal to 8 electron. So all of these achieve a stable configuration, which is outermost shell must have 8 electrons. Example like neon. Neon is 1s2 to s2 to p6. So valence electron is, the valence shell is 2. So valence electron is 8. 1s2 to s2 to p6. So that valence shell is 2. Valence electron now is equal to 8. Right? So this is stable configurations. achieve 4 pairs and 8 electrons. Next is how do we attain the octet configurations? By forming the chemical bonds or by forming the chemical bonds lah. So how the atoms like a noble gas, how the atoms other than noble gas to achieve stable configurations? So they need to do a chemical bond, either share the electron, either accept the electron, either donate the electron. They can do that way in order to achieve stable configuration. So which is make a bond. So what is chemical bond? Chemical bond is actually the bonding between the elements, like Cl. So this is chemical bond. Okay. So how do chemical bonds occur? Bond occurs so that atoms they have opportunity to achieve stable configurations, isn't it?
Yes.
Because stable configurations are the lowest energy level, so that's stable configuration. If high energy level is not stable because excited state. So to achieve to make a bond, they have 3 types of bonds, which is through ionic bond, covalent bond, and metallic bond.
All right, the metallic is the new one.
Yeah, metallic is the new one. Okay, how chemical bonds was formed? By gain or loss, or by sharing the electron valence that might occur in the atoms. So remember, keep in mind that bondings always involve the valence electron. What shell involved in the chemical bonding is a valence shell, valence electron that share the electron or transfer the electron. The one is chemical valence electron. Okay, types of bonding. First one, we look at the first types of bonding, which is ionic bond. So ionic bond must be metal and non-metal. One donate and another one accept the electron. So the the definitions, ions form from the atom by transfer of the electron between metal and non-metal. Example, Na is metal, Cl is non-metal. So NaCl form through ionic bonding, very strong bond, NaCl. And how they do the bond? They transfer the electron because Na plus Na plus electronic configuration 1s2, 2s2, 2p6. While the Na atoms, Na atom is 1s2, 2s2, 2p6, 3s1. So one electron transfer to Cl. Cl atoms having 1s2, 2s2, 2p6, and 3s2, 3s2, 3p, 10, 12, 17, isn't it? 5. 10, 12, 7. Minus proton number for chlorine is 17, isn't it?
I think so.
Okay, 17. Then valence electron here is 7. Yeah. So that for atom Cl, this is valence electron configuration, while Cl minus 1s2, 2s2, 2p6, 3s2, 3p6. Because accept one electron, achieve a Cl minus stable configurations. Alright, so because Na having a valence electron 1. So 1 will transfer to the, how to draw the, I draw here. How many orbital for Na? At first Na they have 1, 2 and 3. 1, 2 and 3. Okay. So 1 electron transfer to Cl. Cl, how many orbital? 1, 2, 3. 1, 2, 3. Cl. This is Cl. Then we transfer to electron here, because at first Cl having 17. Okay. So Na, when donate 1 electron to Cl, Na now become Na plus. While
Na plus.
Cl accept
Cl
1
minus.
become as Cl
Minus.
minus. So that's for the ionic bond. Now we look at the covalent bond. Remember, ionic is between opposite charge, positive and negative, like NaCl, Na plus, Cl minus. Okay, for covalent is sharing the electron between non-metal and non-metal. So covalent bond is weaker compared to the ionic bond. Ionic bond is stronger. Intermolecular forces between intermolecule. Okay, so example Cl2, Cl share the electron, Cl1, 2, 3. How many? 1, 2, 3. 7 valence electron. Okay, so share the electron with another Cl, become share 1 electron. Okay, so Cl share with Cl1 become Cl. This 2 electron become 1 bond, single bond. This is a covalent bond. Alright, now we go to metallic bond. Metallic bond is between metal and atoms. Always result with the complex ions like copper. Example, copper cyanate, CN6. This is complex ions, complex metals, CuCN. And next example, CuCN. For combinations of metallic bonds is a combinations of metal with the atoms always result or form the complex ions. This is complex ions.
Wait,
Complex
so
metal.
these are examples of metallic bonds?
Yeah.
CuCN.
So,
What's Cn?
Cn is cyanide.
Cyanide?
Cyanide. Cyanide.
Very, very good for health.
Cn minus. Okay, so the always found in metallic bond found in metal because metal. So each atom is bonded to several neighboring atoms like Cu bonded with 6 Cn, and then bonding electron are delocalized. Delocalized mean that.
What does delocalize mean?
Okay, delocalized means that it's not fixed in one place. It's always move, like benzene. You remember structure of benzene?
Yes.
Okay, benzene can delocalize, isn't it?
It can? I never knew that.
Yeah. So when delocalized, it will change the positions of double bond. change positions for double bond. So this is what is meant by the bonding of electron can delocalize, can move.
Okay.
When it's moved, it will form a resonance structure.
Oh, wait, so there's a special way to draw a diagram, right?
I think I have slide. I have slide. I show you the. So the metallic bond, of course, high electrical and good conductivity, electrical conductivity because metal, isn't it?
Yes.
Metal is a good electrical and heat conductor, and high melting point and boiling point because metal solid, high melting point and boiling point. We need high energy to cut bond, to cut the bond. So high melting and boiling point, and also metal is luster. Okay, luster is like a shiny. Okay, then types of bonding. This is the example like I told you. Benzene can delocalize its bond, either move to here or here and move to this and then
Wait.
become
What's the
this.
red and the blue electron things?
It means that it's combined, it's a form of bond, new bond.
So that means like the red one is the
This is
X.
for okay, not just showing the example for you. What is the localize of the electron?
Okay.
You can read this letter. Okay, this is three models of chemical bonding like we discussed earlier: ionic bonding, covalent bonding, and metallic bonding. So covalent bonding is between Na plus, Cl minus, ion, cation, and anions, and then form many ions here. And then for the Cl minus, Br minus, this is Cl minus, Br minus. This is between non-metal and non-metal, isn't it? So this is covalent, form covalent bond, and metal with the many atoms. So this is the metallic bond.
Wait, so the first one is the metallic bond.
The first one is ionic bond.
Okay, the first one is ionic bond. Second one is covalent. The third one is metallic.
The third one is metallic bond.
Okay. Can't really look at the difference, but okay.
The
last picture is a metallic bond now.
You can't hear what. Miza, type what you want to say, Miza. I'll say it for you.
Again?
We can't hear you, brother. Your mic is bad.
Okay.
Okay, now we go to the next slide, ionic bonding. Now we're focusing on how to calculate enthalpy in ionic bond. This is the main subtopic in chapter 8, how to calculate the energy of the ionic bond. Okay, consider the reactions between sodium and chlorine here. So the formations, the enthalpy of formations for the chlorine and NaCl, enthalpy formations of NaCl from its elements is equal to negative 400 kilojoule per mole. So this is exothermic. Exothermic because release heat. This is exothermic. Release heat means that negative lah. Release heat. So the reaction is exothermic. This is the reactions of formations of the element NaCl molecule from its elements, from its atoms here. Okay, exothermic. So the formations of exothermic is exothermic means that release heat. So when we fill the beaker here, it's feel hot. If we touch the beaker, it feel hot. That's why heat is being released. Okay, so the formations of NaCl here. Na has lost one electron. This is arrow. Na lost electron, and A to Na plus electron. So lost one electron. Cl minus gain the electron. Cl gain the electron to form Cl minus. Then electron lost by Na is gained by Cl. That's why we got NaCl. Okay, so we look at in terms of the stability. Na plus more stable compared to Na atom. Once is received or dot A, when we donate one electron, it becomes stable configurations like H neon. And for Cl minus is stable configurations than Cl. So it's possible to form Cl minus rather than Cl. And I'm not showing you this thing lah. You can say that you can draw again and to understand this part. Okay, I can conclude from here. Na 1s2 2s2 2p6 3s1. This is not stable, not octet configuration, isn't it? Not achieve octet configurations. Once it's donate one electron, then it achieves stable configurations, octet configurations. For Cl minus, at first Cl atoms, this is not stable or not achieve octet configurations, but once it accept one electron to p orbital p shell here, now become octet configurations already.
I see.
Okay, so so sodium chloride has a crystal structure, which is rod salt structure. Each NaCl is surrounded by 6 Cl minus, and Cl ions is surrounded by 6 Na plus. We call it tetrahedrally bonded with the each atoms here. You look at this figure. What is meant by this sentence here? Look at Na. Okay, Na here is bonded with 6 atoms Cl. 1, 2, 3, 4, 5, and 6. Can you imagine here is there one other one 6, and then here this is 4. 1, 2, 3, 1, 2, 3, 4, 5, and 6. And same goes with the Cl. Cl bonded with the 6 Na plus. 1, 2, 3, 4, 5, and 6. 6A. This showing one unit cell. They have 100, even 1,000 of unit cell of NaCl. Okay, this ionic bond is stable. Because they have the attraction force between the ions, or unlike charge, positive and negative. Okay, the attractions draw the electron together by ionic bonding. Okay, this is the rod salt structure for NaCl. You can see Na is surrounded with 6 tetrahedral of the Cl minus, and Cl minus surrounded by the 6 Cl Na plus. This is 3D structure and one unit cell. Okay. So remember, NaCl is the exothermic. Exothermic means that release heat. Energy that been released, we call it as a lattice energy. Lattice energy, because Na and Cl is a structure, and Na and Cl is a structure bonded. So this is stable, not excited, so low energy. But single Na, which is Na plus Cl minus single, is very high in energy. So from high energy to low energy, release the energy, excess energy. So you can read ionic are stable because of the attractions between the ions of the unlike charge and strong interactions between the ions. Okay. Alright, so the energy that we call lattice energy just now, energy that released from the exothermic reactions of NaCl, we call it as a lattice energy. So a lattice energy is the energy required to completely separate 1 mole of solid ionic compound into its gaseous ion. Example here, NaCl solid dissociate or separate to its ions. So this is lattice, delta H lattice or lattice energy. This is lattice energy equal to 788 kilojoule. The value is given. The value is given. Okay. So we any questions? Any questions on this? Until
Is it okay? How do we count the lattice energy, Miss?
Okay. This value is provided. Okay, how to calculate the lattice energy? We have a step which is we use Born-Haber cycle in order to get the lattice energy here.
I see. Okay.
We look at after this the Born-Haber cycle, and we also apply the Hess law, which is a series of steps in order to find the lattice energy. Good question.
Okay.
Basically, lattice energy ni can relate to endothermic tu kan?
Yeah.
Yeah.
Dissociations of NaCl, what amount of energy that require to separate this ionic bond to NaCl and to Na plus and Cl minus. Okay. Is there any questions? Any? No. If no questions, then we continue. Okay. Alright. So until here, I want you to understand. Like Yang Wei asking me how do we determine this lattice energy? Okay, that's very good questions. Alright, before that, we look at first about the lattice energy, the fundamental of the lattice energy. Okay, the magnitude of lattice energy depends on the first one is charge, second one is size. Charge of the ions like NaCl and Na plus and Cl minus. So charge Na plus is a Q1, Cl minus is a Q2. So this is charge. And size of ions, size of ions is like if Na plus, Ca2 plus. So what happened to the size of ions when Na plus go down the group 1 and Cl2 plus go down the group 2, and then the arrangement of the ions in this solid. So the potential energy E, we can calculate between the two particles, the two charged particles, example Na plus and Cl minus. So we can use this formula K Q1 Q2 over D. D is distance between their center. Like NaCl. So between the distance between Na and Cl, this is D lah. Q1 and Q2 depends on charge. Na plus 1, Cl minus 1. So Q1, Q2 is 1, 1. And K is constant. K is the column constant or electric force constant. The value is 8.99 exponent 9 joule meter per column squared. This is a constant. Okay. So the trends in lattice energy, this is lattice energy values, while the here is the showing the comparisons between this lithium group 1 and group 17. Okay, down the group and down the groups.
Miss, what's PM stands for? purple or
Which one?
PM on the trends in lattice energy.
PM. Where is PM? Oh, here, PM. Picometer.
Picometer. Okay, alright.
If ppm, ppm part per million. So this is picometer. Because of this is size of the Li plus and A plus, K plus here.
Alright
Okay,
then.
so you can see this lithium, the size is 76, isn't it? 76 picometer, and A plus is 100, even bigger, and then down the group even bigger and bigger, isn't it? So what happened to lattice energy?
The lattice energy increases.
Atomic size decrease, increase lah, down the group. Atomic size down the group, from top to bottom, atomic size become increasing.
Yeah.
And then what happened to lattice energy?
Decrease.
Lattice energy decrease. Because remember the formula, E equal to K Q1 Q2 over D. What happen if distance, which is the radius here, become higher? What happened to energy? Lower, isn't it? Distance higher, energy is lower. That's why atomic size increase, lattice energy is decrease.
So it's inversely proportional.
Yeah.
Okay.
Same goes with group 18. Group 18, down the group from fluorine, chlorine, bromine, and iodine, the size down the group increasing, while the what you call the lattice energy, lattice energy is decreasing. Okay, same like the lithium here. Group 1. Okay, then look at the example 1. Arrange the following ionic compound in order of increasing lattice energy. So how do we identify which one is the highest lattice energy and which one is the lowest lattice energy? Okay.
We have to see the charges.
Yeah. Alright. So the Na and Cs same group 1, isn't it?
Yes.
Na plus, Cs plus, Ca2 plus. So CaO, Q1 and Q2 is higher, isn't it? Compared to Na plus and Cl minus, Cl plus, Na plus and Cs plus. So the CaO is highest in lattice energy. Alright, now we look at these two. But because these two same charge, same Q1, Q2, thus we look at in terms of radius. What happened if we go down the group 1 just now? What happened to the radius? Radius and lattice energy. Atomic radius become increasing. What happened to lattice energy?
Decrease.
Decreasing.
So which one first? Na or Cs?
Na.
Because increasing.
Yeah,
Increasing means that lower first.
Oh wait, lower first. Then lower lattice
CS.
energy, right? CS
Lower
first.
lattice energy, Cs first. So CS1, then followed by
Na.
F, and followed by
Cal. Hey, we did it.
Yeah.
Q1, Q2.
Q1 and Q2.
Okay, Q1 and Q2 we determine from just like CaO, Ca2 plus and O2 minus, just for both ions here. look at the formula KQ1, Q2, and then D. What happen if we have higher charge? Means that higher energy lah. That's why we choose CaO first, the highest energy compared to these two. These two having lower charge and there's lower energy, isn't it?
Yes.
So we choose this as the highest lattice energy, and then we look at these two because same charge, same Q1, Q2. We look at in terms of radius. And A and Cl down the group, what happened to radius? Radius increasing, thus energy become decreasing because inversely proportional. Did you is that clear?
Yep, it is. Anyone else got any questions or like don't understand?
Yes.
Okay, cool. What do you not understand?
Okay, and I have a question. No?
Miss.
Huh?
Can you explain again about NA bigger than CS?
Which one?
The NA is have bigger lattice energy than CS. Can you explain again?
Oh, okay.
Okay.
Okay, Na and CS. Look at this graph. Lithium, sodium, potassium, rubidium, and cesium, isn't it? Group 1. So what? Go down the group, top to bottom here. What happened to size? Size become increasing, isn't it? The distance between the ions here become increasing. So D is higher, energy become lower. So which one is lower in energy, CS or sodium?
Yes.
CS. So that's why we put in front here CS first, then followed by Na.
Okay.
Always remember this formula lah in order for you to answer this question. Always remember this formula. Then you can do all the questions regarding these sections. Okay. If you cannot compare in terms of charge, yeah, you compare in terms of radius, atomic radius with the energy. Okay, so the next example, explain why Mg greater than Ca greater than strontium. Magnesium, calcium, strontium. So down the group, size, atomic radius increasing, lattice energy decreasing. Okay. Explain why magnesium is greater of what? Greater what? Greater lattice energy lah put. Okay. Magnesium is greater than Ca, greater than Sr. Okay, so in terms of lattice energy. Right. So Q1, Q2 are same. What is mean by Q1, Q2 are same? Because Mg 2 plus, okay, Mg 2 plus, O2 minus, Ca2 plus, O2 minus, Sr2 plus, O2 minus. Same, isn't it? The charge is same. So Q1 and Q2 same. Same. And radius, atomic radius different. Atomic radius different because down the group become increasing, size increasing. When size increasing, lattice energy decrease because inversely proportional, E equal to K Q1 Q2 over D. Higher the size, atomic radius, lower the energy. Right. So all the three elements here from group 2, same charge. Radius decrease from strontium, calcium and magnesium, thus decrease in lattice energy. You can see the difference here, isn't it? 3,700 3,400, 3,200. Decrease in lattice energy because of the higher atomic radius of strontium compared to calcium, compared to magnesium. Alright, now we go to the susah. Okay, so we just now Yang Wei asked about the lattice energy. We can calculate the direct lattice energy because it's quite difficult to calculate the value. So direct experimental determinations of lattice energy, delta H lattice of an ionic solid is difficult to calculate. Thus, we need to calculate the lattice energy using a series of steps by indirectly determined from the experiment using Born-Haber cycle. So Born-Haber cycle use Hess law to put the steps together. So Hess law is a series of steps. We add up or sum all of the series of steps in order to get the delta H lattice. Okay, we look at okay, this is a statement by the Hess law. Hess law states that if the reactions is carried out in series of steps, means that delta H for the reactions will be equal to the sum of the enthalpy change for individual steps. So you must add up all the individual steps in order to get the delta H lattice of this from the series of steps. Okay, now we look at the formations of NaCl can direct or indirect. There are two routes, which is direct routes. Formations of NaCl, delta H formation is equal to this value. This is direct routes. If indirect routes, they have a few steps. Step number 1, number 2, number 3, number 4, number 5. So we look at one by one. Please focus this thing, because this is the important. Always come out in exam. Okay. All right. First step is how to get the formations of the lattice of NaCl here. We know the formations of NaCl is equal to negative 410 kilojoule. The value is given later. The value is always given to you.
So this what value is this actually?
This is formations, delta enthalpy of formations for NaCl.
Okay.
Okay. Then after we know the formations of NaCl, then another step, series of steps. First, in order to get Na plus and Cl minus. So how do we get this Na plus and Cl minus? For the to calculate the lattice. Okay, first step you change from here. We know the Na solid, isn't it? So Na solid you change solid to vapor, or we call it as atomizations of atom Na to gaseous state. Na turn to Na solid turn to Na gas. The value is given. This is delta H, change of atomizations of Na to Na vapor. The second step is the after that we got Na gas. Okay, then we look at the Cl. In order to get this Cl minus, we change the compositions of Cl2 molecule to Cl atom. So from dissociations of half Cl2 to half Cl. 2 half Cl means that you have half Cl and another half Cl combine get 1 Cl, isn't it? So dissociation of half Cl2, we get Cl gas. The value is given. This is the value of decompositions of Cl gas. Okay, next step is ionizations of Na gas to Na plus. Remember, first ionizations energy from atom which is in gas to Na plus gas. The value is here. Then next step is formations of Cl gas, because we got Cl already, right? So Cl gas form Cl minus by gain 1 electron. So the value is negative 349. And step number 5, formations of NaCl from ions of Na plus and Cl minus. So Na plus Cl minus gets NaCl. This is lattice that we want to know this value. How to know this value? So this value can be calculated by using Hess law. Series of steps here, you add up together, you add all together this series of steps, then you got the value for the lattice. Or we can use the formula delta H formations equal to summations of delta H plus with the delta H lattice. Delta H lattice is always negative.
I see.
Okay, so this is a diagram figure showing the direct routes, which is formation delta H formations of NaCl. You can get direct from NaCl, dissociate from its atom, its element Na and Cl2, and the value is given. Okay, then first step is atomizations of Na solid to Na gas. Okay, from Na gas, first ionization energy. Step 3 actually first ionization energy. Ionization energy 1. So Na remove 1 electron, become Na plus. Okay, then from Cl2 half Cl dissociate to half Cl. Half Cl means that 1 Cl lah. Dissociations of Cl. This is the value. And then from Cl gases, undergo the electron affinity, means that we accept Cl accept 1 electron, becomes Cl minus. The value is here. And then Na plus with Na plus Cl minus, this is lattice. So this is what we want to calculate lah. Okay. So here are the summations of Hess law from the 5 steps just now. Step 1 we put the values here. Step 2, step 3, step 4, and lattice. So the 376 is the total, is the summations of this. Summations of delta H here is a 376 delta H lattice. That's why I give you the formula delta H formations equal to summations of delta H plus with delta H lattice. Then you will get the delta H lattice value. So delta H lattice value is equal to 787.3 kilojoule.
Yo, who's removing me from the meeting like again and again?
Oh, first time ah.
Someone keeps removing me from the meeting. I can't hear what Mrs. said.
Okay.
Lag. Yeah, lagging.
Nah, I'm not lagging. Someone's just removing me from the meeting again and again.
Bro, aku jadi tadi time met too much lag and then suddenly got kicked out.
Okay,
Clearly tells you
I
someone.
follow. I follow until here.
Yeah. Yes, miss.
And also clearly someone continues.
Yami, you can check your connection.
It's not my connection. It's someone muting me, miss.
Oh.
Yeah.
Alright. Is there any questions that you want to ask about the Born Haber cycle? Okay. If no questions, I give you one exercise about this topic. We try to do it. We try to do it together. I stop sharing this. Just okay, where's my whiteboards? Okay, can you see the whiteboard right now? Microsoft Whiteboard.
Yes.
Yeah, I can see the whiteboard.
Alright, this is the kind of questions looks like for the Born Haber cycle. Okay, using the values given in the table, construct a Born Haber cycle and calculate the delta H lattice for CAF2. So how to do it? Okay, we try to construct a Born Haber cycle. First, CAF2. Given here is CAF2. And then also give you the formations for the delta H energy for each root here. 1, 2, 3, 4, 5, and 6. Alright. So we want to calculate delta H lattice, which is CA2 plus with F minus to get CAF2. CA1 F2, and this is delta H lattice that we want to know. So how to calculate this delta H lattice? You are given a series of steps as law here. So you construct a Born Haber cycle. How to get this CL2? First try to look at the formations of CAF2. Okay, formations of CAF2 means that enthalpy of formations means that when one mole of compounds here is formed from its element. So Ca elements plus with F2 elements, Ca solid, F2 gas, and we get the CaF2. So this is delta H formations. Value is negative 1220 kilojoule per mole. Okay. Now from here, Ca solid plus F2 gas. Then you look at what as you have used this cancel, so you can cross this out. Okay. Right. Then Ca solid. How to change into gas? How to change to gas? So the atomizations of Ca. Atomization of Ca will get Ca gas. This is delta H atomizations. Value is equal to 179 kilojoule per mole.
Absorb energy to.
And then the rest here you just copy back F2 gas. Alright, so how to get the you have used this to cross it out, and how to get Ca. We are now Ca gas. So Ca can undergo first ionization energy, isn't it? In order to get this, this is the main way, the main route that we want to achieve, the main target. Okay. So in order to achieve 2 plus Ca, right now we are in the middle of the way to achieve this. So we undergo first ionization energy and second ionization energy in order to get Ca2 plus. This is gas, and here is delta HIE1 equal to 590, and then another delta IE2, which is equal to 1150, and then we got Ca2 plus, right? This is copy F2. Yes, right. So we have settled with the Ca. We have got already this Ca plus in order to form lattice, delta H lattice is F2. And how to find this? How to get this F? We use the from here F2. So F2 gas will undergo the F2 gas will here is F here. Okay. One F2 will dissociate to F. Okay. So F here will dissociate to I think I put here F2 gas dissociate to F. This is delta H dissociations, which is 100. Delta H dissociation means that we separate F from F gas. And then how to get F minus? So F minus, coba balik. We have settled with calcium F2 undergo delta H dissociations of F2 if F2 equals to 158, then we get F gas. Alright, then how to get F minus? So F minus is from delta first electron affinity of F equal to negative 348. Then we one F
Miss,
and
you're
here
lagging.
is 2F.
Miss,
F,
Miss, you're lagging.
hello?
Yeah, lagging.
Tak lagging lah. Mana lagging?
Lagging. My whole MS.
Can you hear me, class?
No, I can't.
Eh,
It's not
continue,
you
miss.
lagging.
Continue, miss.
Can you hear me? Sure.
Yes.
Yes, Miss, you're not lagging.
You're not lagging.
You're not lagging.
Are you follow?
Continue.
Until here, are you follow, isn't it?
What?
Ulang balik.
So the F first electron affinity means the F will gain the electron. Remember the EA electron affinity is the tendency to accept the electron, become F minus.
Is that pula?
Plus electron. How many F is 2?
Say what?
Two
And what?
electron.
And what?
So 2F, not 2, because here is 2F. In order to get 2F, so 2 electron, that means you need 2 times with 2. So we have settled with the roots here. Then we find the delta H. Delta H is equal to summations of delta H plus with negative delta H lattice. So delta H formations is equal to negative 1220. Summations of delta H is 179 plus with 590 plus with negative 1150 plus with 158 and plus with 2 times negative 348. Okay, so 179 plus with 590 plus with 1150 plus with 158. The 158, which one? 158. Here. And plus with 2 times negative 348. And last one is lattice. Plus with lattice, negative delta H lattice. So, what's the value? Total all this together, what's the value?
Total of this is, let me count.
Don't forget to times with 2 because 2 formations of 2F minus. Here is 1. So you need to times by 2. This is formations of 1F. 1 is electron affinity, means that you need to 2.
I got 1381.
Okay, 1, 3,
81.
and then delta H lattice equal to plus 1220. What is the answer? Around 2000.
2600.
2601. Good. Kilojoule per mole. But this is the answer. Okay. If questions given like this, then you need to construct a Born-Haber cycle here, and then find the value, find the delta H lattice. Yeah. Okay. Any questions?
No. Oh wait, isn't it supposed to be negative, miss? Or is it
What?
positive? The n value.
Which value?
The lattice energy.
Yeah, that is always negative.
Oh, okay.
Okay, for you to be more used more accurate theory of fundamental, you use in order to indicate the energy, the negative and positive in front here. Negative, you draw down arrow, for positive, up, positive. It is positive.
Miss,
Uh-huh.
what does enthalpy means again?
Enthalpy is energy.
Like why calcium it turns to gas from solid to gas?
Because atomizations, enthalpy of atomizations of atom Ca will form Ca gas. Okay. You try to refresh that what is mean by the enthalpy of atomizations. Enthalpy of atomizations means that energy that you require to remove 1 mole of electron from 1 mole of gaseous atom. Okay.
Okay.
So in order for you to understand more, you try to find out the definition for each term here. You have to study this electron affinity. What is electron affinity? Ionization energy, atomizations. Okay, dissociations. I always mention dissociations of water, dissociations of NaCl. Dissociations means that split or separate from the molecule. And formation is formations of compound or molecule from each element. Electron affinity is the when accept one electron, the ability to accept one electron. So that's one is electron affinity. ionization energy is then what's the value of the tendency to remove the ionization? How hard or how difficult? How difficult or how is to remove the electron? Is the ionization energy. Alright, so if no questions, then I so I stop at this right now.
Okay.
Right now, 1:30, isn't it? 1:20.
1:20, yes.
Yeah.
Okay, so I start at this slide. I try to find out the exercises. Then you try to do the exercises regarding the Born-Haber cycle.
Alright.
Okay, so we continue next week. Covalent bond.
Attendance.
Attendance.
Attendance. Okay.
Yang tadi tu yang fluoride ionization tu we have to multiply by 2 for the energy negative 348, right?
Actually, now you ask your friend. Yes, Mirza, can you repeat your questions?
The earlier part, the calculation, the fluoride ionization energy we have to multiply it by 2, right? Because there's 2 moles of fluoride.
Yeah.
Right. Okay.
Because formations of 1 mole need around 348
Alright.
kilojoules.
Nice.
2 mole, that times by 2.
Alright. Thank you. Can life survive? Attendance.
I have sent the attendance.
I'm freezing. My MS is freezing.
Firza, did you change mic? You actually got better.
Yeah, I changed from my headphone to the iPhone earphone.
Yes, this is the good one.
Yeah, this is a medium quality.